Ionic compounds prefer to dissolve in water rather than in nonpolar solvents. But some ionic compounds don't dissolve well in water either. We want to be able to predict ahead of time whether an ionic compound is soluble in water. And for that, we turn to what are called the solubility rules. There are 5 general rules for ionic solubility. We start with ions that make a compound soluble. First, compounds of ammonium and group 1A ions like lithium, sodium, potassium, and so on are soluble. Regardless of what anion is present, compounds with these cations are always soluble. Second, compounds of nitrate, perchlorate, chlorate, and acetate are always soluble. If you think about how many metals there are in the periodic table, knowing that many have more than one charge, there are well over 100 monoatomic cations. When they're paired up with these anions, they are always soluble. Third, compounds of chloride, bromide, and iodide are soluble. But unlike the first 2 rules, which have no exceptions that we know of, there are some exceptions to this third rule. When these anions are paired up with silver, copper 1, thallium 1, mercury 1, and lead 2, the resulting compound is insoluble. The mercury formula is written kind of funny, Hg2, 2+. Mercury 1+ ions like to come in pairs, with the overall charge of 2+. Notice all of these cations are at the right-hand end of the D block or in the P block. This suggests considerable covalent character in the bonds they form with these anions. That might be something you consider in a future chemistry class. Notice also that fluoride is not included here. Its solubility characteristics are not like the other halogens. Fourth, compounds of sulfate are soluble, with the exception of calcium, strontium, barium, and lead 2. So, what makes a compound insoluble? We are going to assume that compounds without any of the ions listed on our soluble list are insoluble. It's worth making some comments about these rules. When we say that a material is soluble, that means that its maximum concentration is at least 0.1 mole per liter. If you can't even get that much into solution, then the material is considered insoluble by these rules. Which of course means that the term insoluble does not mean 0 dissolves. It just means less than 1/10 of a mole dissolves in a liter of solution. Also, just because a material is soluble by our rules, it does not mean that it is infinitely soluble. There is still a maximum solubility, at which point the solution becomes saturated, but that concentration is above 0.1 molar. Know also that our solubility rules are for room temperature. Heating up or cooling down a solution can change its solubility characteristics. Finally, you only need one of the 2 ions to be listed on the soluble list in rules 1 to 4 in order for the entire compound to be soluble. Let's see how these rules work with some examples. First, is NaBr soluble? When it dissolves, sodium ion is produced, so by rule 1 this compound is soluble. Bromide is also produced, and by rule 3 the compound would be soluble also. Remember, you only need one of the 2 ions to be on the soluble list. Our next example is iron 2 nitrate. Iron 2 ions are produced, which do not appear in any of the soluble rules, so we might be tempted to say no. But nitrate appears in rule 2. So by rule 2, this compound is soluble. Since we only need one of the 2 ions on the soluble list, this compound is soluble. Our next example is copper 2 hydroxide. Copper 2 does not appear on the soluble list. We don't find hydroxide on the soluble list either. They both fall under rule 5, so we conclude that copper 2 hydroxide is insoluble. Our last example is lead 2 chloride. Lead does not appear under any of the soluble ions. Chloride ion does appear in rule number 3, but lead is listed as one of the exceptions. When lead pairs up with chloride, it is an exception to the soluble rule, meaning that this compound is insoluble.